All right, so good morning, everyone. Welcome to this special colloquium. Today we have the pleasure to have with us Chirality, Professor President Tasman. And since Paulo knows him very well, I kindly asked Paulo to use Cyriaque, so please.
Hello, good morning, welcome everyone. So I have known Cyriaque for a long time. It's the third time he comes here, and the first two times was still a graduate student, and since then, as of course, became a well-known scientist in several domains. He's now a research director of CNRS at the Institute of Supramolecular Science and Engineering at the Strasbourg University, and has been there for some time now. And he's well known for his work on stochastic thermodynamics, chiral forces, and more recently he pioneered this new field of chiral thermodynamics, which is really very well known. Pioneering this field where take together this concept from stochastic dynamics and chiral optical forces to have a new and exciting result. He's going to talk about some of these results today. I thank you very much, Cyriaque, for coming here. He's going to be here until next Tuesday. Okay, so if you approach him with questions, and also he's coming here, I have to say, this collaboration capsule that we have for other 3 years. So I hope we'll have the opportunity to go again during this time. Coming about oh yes, and yes, that's a good information. He's on the third floor of the new building. It's the office with the name Marcelo Barbosa. So, on the top floor.
Very much, Paulo, for this nice introduction. So, very nice invitation. I'm very happy to be here. So, as Paulo mentioned, I'm here on the framework of the project. It's an important exchange program. So I'm going to tell you some results and discussions on this problem of chiral light matter interactions. The very general things, trying to understand why this topic is so many people in different areas. And it's clear that when you look at the manifestations of chiral light, chiral matter interactions, you are facing fundamental issues that chirality is blending. On the one side, chirality is a very efficient way to connect some specific concepts that we are confronted with in optics every day: dimensionality, participation, and this is at the heart of some very interesting optical phenomena, spin momentum locking phenomena. On the other side, the chirality also entertains nice connections between forces, motion, and thermodynamics. This system of chiral optical forces, the new chiral separation schemes that many people, and in particular here in are working on. So I think this blend explains the recent surge. I'm sorry for the miss. So there is a recent surge in these studies going from optical spin-orbit interaction. Sorry, silence. This is the problem of enhanced Q optical spectroscopy, or you can tailor optical fields to improve the sensitivity on chiral detection. And also recently, people are investigating what is called chiral quantum sensing. So you go to quantum regime, and you want to exploit chirality as new means of separating superpositions of chiral molecules, coherent superposition. So there is a lot of activity in this topic. And in my talk, I would like to address maybe 3 examples that I think are combining problems. The first one will be focused on chirality. Then I will discuss more in depth this problem of spin momentum blocking, and in particular in surface plasmon optics, a perfect template for exploring these effects. And I will finish my talk with discussing some aspects of chiral optical force. So I don't know why I'm sorry for that, but I hope it should not be problematic from those. So I will start with a very simple definition of chirality. It's a very simple one, but it's a very effective one because it gives immediately an operational manner to characterize the chiral system by the absence of mirror symmetry. So if you have for instance, a Jones matrix, characterize the interaction between light and your chiral system, the system will be chiral if that matrix does not commute to the parity of gradient. So it's very simple, and this is very central to many aspects. So the first, of course, the first chiral systems we are very well familiar with are these 3-dimensional chiral system, LCs, which is let's say an optical model for chiral molecules, for instance, sugar, and so the shape of the Jones matrices that we associate with such these matrices are written in the basis of the circular polarized states of light. They are diagonal with 2 diagonal elements that must be different by the sake of the mirror symmetry breaking. So actually, if you operate a mirror symmetry in such system, you go from one enantiomer, left-handed, right enantiomer, right-handed, and the operation is just a mere exchange of the non-equal diagonal elements. And what we call optical activity is essentially the fact that these elements are non-zero. So these relationships are well known for a long time in polarization optics. And in the context of nano-optics, there has been a lot of discussions coming from meta-surface systems. So a meta-surface is essentially a layer which is decorated with complex patterns, totally designed. So for instance, here you have ratings composed of those 4-fold chiral crosses called gammalions, but you can find many more complex shapes, and this has had a lot of activity in meta-surface optics. What is interesting with this system is that you see that the dimensions are obviously reduced. I was just discussing 3-dimensional objects, which whatever you take, if you rotate the objects in a 3-dimensional space, you do not exchange the form of the object. If you go to planar chiral system, the story is completely different, because if you turn around a right-handed chiral object which is planar, if you turn around it, it's becoming a left-handed chiral object. So this connection, this deep connection, will be, of course, in optics very interesting, because it will be connected with the reciprocity. So this is something quite interesting. And so there has been a very interesting discussions on how to interpret the signatures, the far-field signatures of planar chirality in the context of key optical interactions. And there has been some problematic interpretations, which are simple to understand. So when you have a chiral planar object, you have only 2 possibilities. So the object has to be chiral, so no mirror symmetry, but it can be also rotationally invariant. So this is the situation that you have with those crosses. And if you combine these 2 conditions, you are forced to define a diagonal Jones matrix, circular polarization basis. But of course, because of this problem of reciprocity, you have to show that the reciprocity is obeyed. These are all passive systems. You have to equal these two elements. So, in a sense, a planar chiral object with rotational invariance is a very trivial object. Its Jones matrix is proportional to the identity. And one consequence is the absence of. So this has led people to think a bit more about planar chirality and relaxing the problem of, sorry for that, relaxing the problem of rotational invariance. So if you take a completely general chiral object, like a spiral, then things are much richer. And you can show that chirality combined with reciprocity constrains in a very interesting way those matrices. Reciprocity imposes, but the lack of rotational invariance combined with the lack of mirror symmetry forces you to have these two elements non-equal with different modulus. And so when you look at those matrices, there is something quite interesting that shows up, is the fact that the planar chiral object cannot be optically active per se. If you are interested in circular dichroism, for instance, the system will not be a circularly dichroic, because those two elements are even, and you have to look for cross-polarization terms to characterize the system. So this is called circular conversion dichroism, the fact that these two elements will. But what is also interesting with this system is that by constructions, by these symmetry arguments, you can identify that the matrix cannot be unitary. And so this is, of course, very important in optics. So a non-unitary matrix automatically implies some sort of this. And so this is where the perfect candidate emerges. You need a system which are planar, which are anticipative, and there are not so many optical modes, so to say, in optics that are planar anticipative. And one very efficient class or category of such modes are the surface class modes that propagate in the lossy manner on metallic. It's a way, in the sense, it's a way to delocalize spatially losses from 3 dimensions to 2 dimensions. This is really what people have been working. So we use simple examples that we did in the lab in Strasbourg some time ago. So we constructed so this is the data on which then graved by some ionic beam lithography, some Archimedean spirals. The Archimedean character is important, so it means that you have a constant while you enroll the groove around a single central hole. The constant pitch is functioning as a grating. So you can have sharp resonances on the system. So you can expand the resonant plasmon using white light system. And the near field associated with this plasmon will be transmitted through the single hole, which is the only transmitting part of the device. You will observe in the far field structure, you observe very nice resonance. And this resonant mode has specific polarization components that you can characterize. And you can indeed show that non-unitarity and manifests itself with the non-orthogonality of eigenstates. So you generate through the system elliptical states that rotate in the same way, so they are non-orthogonal. And what is interesting is that you can characterize, you can quantify the overlap both as a kind of a measure of the optical chirality of the system. It's a kind of direct measure of the chiral strength. Now there is another thing which is interesting in this system is if you look at the matrix, send the right-handed or left-handed light through such will break the balance in transmission, left and right. So this is the first manifestation of the spin momentum blocking. Depending on the spin and the momentum, the direction of the momentum you are probing these structures, you do not have the same transmission prediction. So this is really something interesting planar chirality. And so if you put a planar system like that in a Fabry-Perot cavity, for instance, you can start to break within the Fabry-Perot cavity the helicity balance that you expect from standard reflections through neurons. So this going on. These going on discussions in quality QED, trying to engineer cavities so that cavity QED could be extended to the chiral domain. And there is this is a very interesting and important paper by the group of Angel Rubio in Hamburg, who started to really develop type of. In Strasbourg, we are currently trying to use those systems what we call polaritonic chiral chemistry, so putting molecules inside such cavities and using the fact that the optical mode is as a preferred helicity, so could preferentially interact with one specific molecular enantiomer and less. So this is the first manifestation of spin momentum. And so I go back to surface Poisson because they are yesterday. They are indeed very simple systems to build those kind of spin momentum. So what is very important when you have a surface plasmon is the evanescent character force of the plasmon. So it's a wave localized to metal field. It's an evanescent wave. But by the sake of evanescence, you have a longitudinal component of the plasmon. It's not exactly, let's say, from the polarization point of transverse field, you have a longitudinal component of the electric field while in the direction of propagation. So it's an elliptically polarized light, and the plane of polarization is the meridional plane. So the plane that is contained within the propagation direction. This is, of course, completely different. It's transversally different from what you have with propagating waves, where the plane is the plane of polarization of transverse. So there is a very important consequence of this. Momentum blocking. First thing is that the spin density associated with plasmon, because the polarization is why you want to propagate it like that, is that the spin density is transverse to the propagation direction. The other thing is that the transversality is locked to the direction of propagation. So if you reverse propagation direction of a plasmon, you immediately change the direction of the spin density. Lock the direction of the spin to the direction of. One consequence of this is chiral coupling. Because you have a spin polarized atom, for instance, systems, but by rotating dipole, you immediately see that the emission rates associated with this be different depending on whether you couple to a, let's say, forward propagating plasmon or a backward propagating plasmon. So you break from the coupling point of view, break the velocity. This is something. The other thing which is nice with plasmon is that it gives a very simple access to geometric phases in optics. So geometric phase in optics is something very simple, which actually combines polarization and local rotation of coordinates. And because the plasmon system is launched at the level of nanostructure, it's very simple by locally rotating nanostructures to reveal this kind of specific. So the example I put here is the simplest one. You eliminate a small indentation that you have made on the field, on which you launch the principal axis of surface plasmon. You eliminate it with a circularly polarized line. And then you do exactly the same thing, except that you have rotated a little bit by an angle phi direction, and then the action of this rotation on the surface plasmon goes up as a phase that combines the angle and the helicity. This is the definition of the phase. This is also very well discussed in this great review by Gustav Miller, spin orbit interactions of light, where they did many examples of this. Now I come back to those extended nanostructures that I presented, those spirals, of course, this argument of local geometric space can be transported all along the nanostructure. And so when you do this, you give yourself the capacity to induce modes which have cumulated geometric faces. And this is exactly what happens actually on spiral. And when you look a little bit details on the kind of model structure that you expect of such spiral, you end up in building Bessel functions with orbital angular momentum. These orbital angular momentum, they stem essentially from the geometry, and which you can control by, let's say, the number of branches used to form the helix. And so in nano-optics, it's a simple way to generate optical vortices from those kind of systems. Again, it's always the same trick. You have only one sub-wavelength central hole that transmits light. You excite a surface plasmon which carry orbital angular momentum, and that orbital angular momentum will be converted in the far field in a way that is completely controlled by the complexity of the work. I was insisting on the fact that those geometric phases can be locally addressed. So we designed a grating square lattice, but you see that instead of using, for instance, a spherical hole, we use small rectangles that we rotate progressively at each step with a different angle in, for instance, along one direction of the grating. So if you have such a grating in metal optics, you know that you can resonantly excite a surface mode. So these systems are known to behave like cavities, like optical cavities in the near field. Now the additional ingredient is that we have along one direction accumulating geometric phase. So the total phase that now depends on one coordinate of the grating. And so the gradient corresponds to an additional momentum that you have to account for in your grating conditions, resonant condition. And you end like with resonant conditions that are intertwining the grating order, the period of the system, period of the grating, and the helicity of the light you are using. And so the consequence of this, again, this is a manifestation of this speed momentum is that if you adjust the conditions so that you are resonant with the light you are using to excite those grating, depending on the helicity of the light you use, the plasmon will be launched, let's say, towards the left or towards the right, in a completely separated and locked way with respect to the grating. And so those systems are forming what is known as, let's say, a spin momentum locked cavities. And there have been recent discussions in the context of quantum optics, which is known as chiral quantum optics. This is again a paper by Peter Lodal describing the mechanisms of chiral quantum optics. And the main ingredient is the possibility to induce spin selective directional coupling of emission by bringing a spin polarized emitter in the vicinity of a spin momentum locked cavity. So this is what Peter Lodal did using quantum dots in magnetic fields. So when you put a quantum dot in magnetic field, you can spin polarize the dot, and the emission of the dot carries a spin angular momentum. And by designing in a very clever way some very precise photonic crystals which can enable this spin momentum locking, they were able to source the emission of the dot one direction or the other, depending on the speed paired by the external magnetic field. And Arnaud Roche-Montel, Della, also showed this in all atoms in this. So these systems were intriguing to us because we wanted to use surface plasmon systems, so to say, to go forward that direction. And so this was the idea that we had with my friend and collaborator, Stéphane Versio. So we have the ingredient for, let's say, the spin momentum locality, which is potash. And the spin polarized emitter we're thinking of are these transition metal chalcogenides in this system, which, for reasons I will explain next, allow to have spin polarized value transition. And so if we are able to combine these two systems, we might use as valid information carriers, which is just the manifestation of this carbon copying. What is interesting in this context is that plasmonic meta-surfaces, so to say, or plasmonic ratings are purely 2D systems, and those transition metal chalcogenides are also planar atomic atoms. I will briefly discuss the system. So this is semiconductors, because they are semiconductors, consist of two atomic layers of chalcogen atoms, which are sandwiching a transition metal, a layer of transition metal atom. And the constraints are such that they form an hexagonal network, and the layers are covalently bonded. Very, very solid that you can actually manipulate on a single layer level very easily. And so by the hexagonal constraint, you have an hexagonal Riemann zone. And the surprise is that you can form at specific values of the Riemann zone, it's K and minus K values. You can form excitons, which are very robust and which actually interact pretty strongly with light. So in the monolayer limit, you have it's a semiconductor with a direct band gap, and the absorption of visible light on such system, for instance, is about 20%, with a very nice resonance around it. It's perfect for combining those systems with metal optics. The microscopic description of the system is very complex. It's a field on itself, but let's say these systems display very strong spin-orbit coupling, so that eventually you end up with bands at the K and minus K value, which are spins. So it means that depending on the helicity of the light produced to form the exciton, it forms selectively for left-handed polarized an exciton in the K value, or if you right-handed polarized an exciton in the minus K value. And this is what is known as a spin value locking mechanism, and this gives rise to many interesting optical features. Maybe the most impressive one is what people call value contrast, is the possibility to form, as I said, selectively excitons in specific values, and by radiative recombinations of those formed excitons, generated spin polarized light. So this system definitely behaves like pretty good spin polarized emitter. You can do this with right or left-handedness, and if you excite the system with a linear polarization, then you form coherently the excitons in both values, which combine radiatively in a coherent manner. So you generate a linearly polarized light. So it's a great system to play around with polarization optics in emission space. And so people have measured for about 10 years ago now those features, very good conditions. What is extremely important to note is that those features are at very low temperature. As temperature increases, you have very efficient scattering phenomena between that eventually racemize the emission of relaxation of. This field is a very active field. We are here in the linear regime and not in the non-linear regime. This is called the polaritonics. So this is what we did in Strasbourg, a little bit in a blind way, but we were just anticipating that those planar materials would couple ideally to a plasmonic material, because a planar material will be completely immersed in the near field of the system, enhancing and maximizing the coupling strength. This is what we did. having in mind that we have a valley speed locking system that we couple to a spin momentum locking cavity, and trying to, by transitivity, trying to generate valley momentum locked. So when you couple such systems, of course, you enter very rapidly the strong coupling regime, so that the both of the system become hybrids between light and matter components, for them dressed states. These are represented by the manner. So you have, let's say, the cavity mode coupled to, cavity mode coupled to the exciton. And surprisingly, indeed, but we were hoping that we were able to generate very strong coupling strength. And then we did the polarimetry of those systems. We're working at ambient conditions or room temperature. And indeed, we were able to see that the emission of the system was flowing in directions which were associated to the valley in which we were creating the exciton. We were transferring the valley degrees of freedom into a plasmonic with a reasonably good fidelity. And also, we were able to maintain the coherence of the two valleys through this, so that it eventually generated a coherent superposition of such polaritonics as we played. The crux, which is still not yet fully understood for us, is that all these experiments were done at room temperature. And if you do those same experiments at room temperature without the plasmonic grating, you will observe absolutely nothing. You will not observe any valley polarization, any valley coherence, completely erased by the very efficient room temperature interval. This is something we are still have to understand, but this is known in this context as it's called cavity protection mechanism. By putting the system in a cavity in the strong coupling regime, protected from decoherence, and this is something. Now I will forget about this. Now I will keep exploring this problem of chiral coupling, but now I will explicitly insert the problem chiral dipole. So, way to describe the most easily of chiral dipole is the combination of an electric and magnetic dipole with corresponding polarizabilities, and the system is chiral if you add to this polarizability matrix non-diagonal elements, so that the polarizability same is not mirror symmetric. So the schematic representation of the system is simply this one, where you have an electric dipole, a magnetic dipole generated from the current inverse by mirror circulation, reverse the direction of the magnet. And so we did some time ago a simple calculation. We calculated the Lorentz force law that taking a general electromagnetic field. Simple classical calculation, the Lorentz force law that is exerted on such a chiral dipole. So we calculated the force and we calculated the force. And the result is very simple. And the simplicity is interesting because the force, for instance, decomposes in three and non-interacting components. One is the standard optical force, the dipole with a given electric polarizability. The system, the real part of this combination is radiant force divided by the radiation pressure. You have the same for the magnetic dipole, and you have a third term, which is completely separated, which is purely associated with the chiral nature of the dipole. And you have exactly the same decomposition form. And so we have been interested in understanding precisely this term. So you decompose this term into a reactive component, the part of the chiral polarization, and the dissipative component. And so when we were doing this decomposition, we ended up in realizing that this reactive force component is associated with the quantity. This is the pseudo-scalar, which writes this way. And the dissipative component, which is the chiral radiation pressure, is connected with another quantity, and it's we come back to these quantities because they have very precise meaning in classical optics. So the first thing we were interested in is the fact that this chiral part of the optical force is solely intertwining the chiral content of matter with the chiral content of the field. So it's an intrinsic chiral force. And so because it's intrinsically chiral, if you change the chirality of the object, you reverse the sign of the force. But you can also change the chirality of the field, and you will also reverse the sign of the force. So you play on both what we call the enantiomeric component, so matter, and the enantiomorphic component of the field on this field. And many people, and in particular here in Rio, have exploited those schemes to develop new ideas for chiral separations and many other things. So this is a simple force calculation made us touch with fundamental discussions that led for many years in classical optics. The question is how to characterize the chirality of a light field beyond the mere, let's say, helicity description of the polarization. And people have come up to find what is called today chiral density, chiral flows, which obey a very interesting expression law, which is very analogous to pointing red. If you use harmonic fields, these quantities are absolutely non-mysterious. The chiral density is just the helicity, the light, and the chiral flow is just the spin density. Work in this field, physics is very simple. In fact, these discussions, they stem from a very interesting paper by 2010 by Tong and Cohen. Tong and Cohen simply did the simple calculation of circular dichroisms. They imagined that you have a chiral molecule, but they were not assuming that the field was circularly polarized. They let the field to be generally polarized. And when they did this calculation, they showed that the circular dichroism term is enhanced by a multiplicative factor, which is just the chiral density. And so this has initiated many work on the surface plasma optics, nano-optics, say the optics, nanostructures, where people were really trying to find situations where the local chiral density of the field be higher than the chiral density that you can associate with circularly polarized light. And the idea was really interesting because these people, and in particular the group of Harald Bisson, they proposed many systems that are very simple to immerse in chiral moieties. Once irradiated, those systems would show hotspots of chiral densities and would then maximize the circular dichroism. So this was considered as a very promising route to enhance the chirological. From the force point of view, for instance, this reactive component of the force is associated exactly with the same chiral density. In fact, the gradient of this chiral density, gradient force. But it is the same quantity. So you can also have the same kind of discussions in terms of force. And for instance, the group of Steve Barnett proposed a very interesting molecular chiral Stern-Gerlach deflectors. So the idea is simple. You have an optical field which has a given gradient of chiral density. So to compare those fields, it's a bit tricky. You have to very precise superposition of fields. Let's say you manage to do this, you manage to use a gradient of chiral density. Then you fly chiral molecules through the system, And so those chiral molecules will start to feel the additional momentum associated with this reactive component, and will deviate in opposite directions depending on their elasticity. Looking in the literature, I realized that this idea, in fact, is not new. It's a remarkable paper from 1996. It's a good lesson because it shows that when you have an idea, the idea are really rarely very new. And I actually had a discussion with Sheikman. He's a very nice old man. Died now, but and he was. They published this paper without knowing if this was interesting or not. And the idea is exactly this one. They were creating those interference patterns where chiral densities was not exactly formulated this way, but this is the idea that if you radiant forces which would depend on the chirality of the molecules they were sending, molecular beams. These people were specially they were sending this paper, which is the other interesting thing about these chiral forces is the fact that if you compare standard optical forces, parallel optical forces, you see a very interesting exchange between linear and angular momentum. So, for instance, if you take radiation pressure, forget about the magnetic part, but if you look at the standard radiation pressure, it's solely determined by the orbital part of the Poynting vector, of the electric Poynting vector, linear momentum. Whereas if you look at the chiral radiation pressure, it engages the chiral flow, which in the harmonic regime is the spin density. So from the, let's say, the linear momentum of the dipole, you have an exchange between the linear and angular momentum of the field. And so these cross interactions give the possibility to use lateral forces, wind forces, left-handed torques, assisted by chirality, which is this ingredient that allows you to turn, in a way, feed the angular momentum into a linear momentum imparted to the interacting. And so to conclude, just flashing a few schemes, experimental schemes, theoretical proposals in this context of parallel optical forces. I think, but you might correct me, I think we still lack totally. This experiment is very clear. This is a very good experiment by Brasselet and Bordeaux, but the thing is that it's not exactly the nano-optic regimes. And it combines very subtle cholesteric systems at the 10 micron size. This is maybe the first demonstration of all optical sorting. And people are fantasizing in reducing scales, which the molecular regimes set. And in this context, optical tweezers are great tools because practically dimensions. Somehow we have been suffering a lot trying to do this. Never managed to have anything. But you have many ideas here, and it's great. And a few groups are moving to the quantum regime. And maybe two interesting examples. This one is, let's say, is adaptation of the Russian-Bödel ideas of the chiral quantum coupling polarized atom to the vicinity of the fiber. But these people, they look at the force perspective of this symmetry breaking mechanism and how modified spontaneous emission induced chiral recoil forces that can be observed. Broken mirror symmetry on each. And in the group of Stefan Luhmann at the University of Kassel, they are trying to exploit chiral Casimir-Polder interactions. So you fly chiral molecules, fabric chiral cavities, which are made of chiral mirrors, and you try to modify the Casimir-Polder interaction. To modify the Casimir-Polder interaction while the molecules are getting So I would like to finish. Oh, yes. So trying to summarize the motives for this kind of research. And I'm finishing by thanking the people working in Strasbourg. A special mention to Louis Direct, PhD student here. Spent 4 years in the lab, starting and of course all my collaborators. Thank you. I have time for some minutes. Sorry, I Yes, this I really do not understand. Very English, you're right. The compounds here are very simple. Let's say, from the semiconductor forget about yes. But I'm not a specialist. Maybe, yes, so probably you are right to say that people must I push.
Now, like we have
I would answer yes, but I think no one has the answer, because in fact no one understands. Let's say from a light matter interaction point of view, those asymmetric reactions where the asymmetry is induced by circularly polarized light. It's very difficult. I mean, maybe I'm going too far by saying this, because, but as far as the papers I've read in this asymmetric chemistry community, so there are the famous experiments by Henri Cagan in the 70s, where they did show that if you so you have a photochemical reaction, if you do that reaction with a circularly polarized light, you can bias or you can induce some enantiomeric excess. So I would say, if you do this linearly polarized, there is no excess. If you do it circularly polarized, there is an excess. So probably you can access the continuous regime as course. Then you take a matrix, let's say chiral density, and you, but I don't know. I mean, I haven't seen any model of the precise interaction. Yes, yes, that's no, and never been done. And there are very few experiments. There are very few reactions, actually. So this paper is still a milestone. of concepts. So you can find thermodynamic interpretations, but it's a point. Yes.
Question? What are some technological
Let's say the dream would be to be able to have these forces acting on the molecular scale. Because then you shine light, a racemic mixture, and separate the population left and right, left and right and the molecules. So it's a all optical sorting system. Technologically speaking, incredible because there is only one technique today used for separating chiral molecules. It's color chiral chromatography. It's used at the industrial scale, but it's a very complex technique, very expensive. If you find an all optical way, of course, when you go to the molecular scale, you are immediately first to do drastic reduction of force. And of course, chemists work well by motivation. So it's a loss unless you find a very clever tricks to isolate chiral component, the rest of
any reasons? Thanks.
Thank you.